Yeah. So my name is Mark Brown. I'm a principal program manager on the Azure Cosmos DB team. I've been with Microsoft since February of 2000, on and off, I guess. So about 20 years. I'm originally from this area. I actually lived in County in Laguna Beach and Costa Mesa for, I don't know, most of the 90s. And then when Microsoft recruited me and hired me, they moved me up to the Redmond, Seattle area. I traded a nice ocean view for a view of a bunch of trees, and I vowed one day I would come back home. And what do you know? COVID happened, and Microsoft decided that, hey, you've all been working from home for the last whatever year, 18 months anyway. When we go back to fully open, if you want to continue doing so, just right on ahead. So as I've never quite gotten used to the winters in Seattle since I'm solar powered, I decided to move back down here. And so now here I am in Irvine, and I'm enjoying the nice weather. Well, actually kind of a hot weather, but it's better than Seattle. Actually, not today, it's not, but it's normally better. So anyway, I'm going to talk to you about data modeling and partitioning in Cosmos DB. If you're not familiar with a database like Cosmos, Cosmos is what we call a distributed, horizontally distributed NoSQL database. And there's some very kind of special things you need to learn and understand when modeling this. 9 times out of 10, people approach this database and think of it like they can model data and use it like a relational database, like a SQL Server or a MySQL. And in nearly every case, that's not the case. That's not true. And in fact, you can get into trouble, at least in terms of performance and scalability and cost. So this talk we developed to help people understand the concepts necessary for data modeling and understanding kind of the best practices surrounding that. And what we're going to do is apply this to a real world scenario, or at least it's contrived, but it's real enough. And what we'll do is we're going to take the AdventureWorks database, or at least a subset of that, and we're going to migrate that from a relational database, as it is, to a NoSQL database, to a database that can scale. And hopefully you'll understand kind of the differences between these two types of database, because understanding these concepts in modeling and partitioning is going to help you better understand the service and understand how you can design for it, and making Cosmos maybe a possible database for upcoming projects. So what is Azure Cosmos DB? Well, it's officially Microsoft's NoSQL database on Azure. But what we really mean is, as a NoSQL database, it's both non-relational and horizontally scalable. So let me break that down for you. So talking about the horizontal scale aspects of a database like Cosmos DB, unless your workload is really small, with just a few amount of requests or a low amount of data and requests, your data is going to be spread over lots of different servers, right? This is what it means to be horizontally scalable, is you add more servers to your database rather than increasing the size of the VMs that you work with. Now, in Cosmos, we abstract all this away, but fundamentally, you're reading, writing data across a cluster of servers. And this is better known as scale out. And it's how we achieve horizontal scalability in a database like. Now, the nice thing about this is that with a scale out, you theoretically can get unlimited storage capacity. I mean, it's only limited by the amount of servers that you can actually address within a data center or within a cloud or within a region. It also provides you unlimited throughput, because each server you're adding not only adds additional capacity, but it also adds additional compute power, right? You get additional CPU and IOPS and memory that come with that additional compute on top of there. So you add the ability to handle additional requests as that data comes in. Now, Cosmos is also non-relational. Now, when you're working with relational databases, you have the ability to define relational constraints between the entities you're storing. And this lets you do things like create foreign keys and perform join operations across these different entity types that you have. A database like Cosmos doesn't have any of these types of things. And the reason is because doing so, putting like referential integrity or locks on data that are stored on different servers can have really enormous impact or implications for things like availability. For instance, say one of the servers ends up going down, or it has some kind of hiccup or some race condition. You wouldn't be able to operate on any of the data because you would not be able to put a lock on any of the data in there. So this could have a big impact on the performance and availability of your database. Now, a database like Cosmos is actually designed to be predictable in terms of its performance. And because of that, there's a conscious decision with a database like Cosmos to do away with things like putting locks on data and stuff like that. It also helps with write throughput and performance because you're not locking data and putting locks on data when you're trying to ingest a lot of data. And for databases like Cosmos, this is fundamentally why this genre of database was created to begin with. When you had companies like Facebook and Google and others, and even Amazon, these all came about kind of with the advent of the cloud, or the advent of kind of internet and growing at scale. I think there was a famous story about Twitter trying to, or was it Facebook trying to scale out MySQL, and they just couldn't do it anymore. So that's where something like Cassandra would come from, and other NoSQL databases as well that have been hatched out of companies like this came about because you couldn't take a relational database and make it do internet scale types of things. You also had, with the advent of the cloud, the ability to be able to survive kind of localized or regional failures, which means that they're distributed in that sense. So you have to replicate data, and you need mechanisms to be able to replicate that data and understand its consistency and all of that. So that's kind of why these databases are here. And so the reason they're different, it's not that you can't put locks on data in different servers. It's because they're designed for fundamentally different kinds of workloads and to solve different problems within the cloud. Okay, so Cosmos DB is both horizontally scalable as well as non-relational. And it provides that, because it's designed for that kind of high performance, high availability scenario. So is Cosmos good for relational workloads? Well, yes, actually it is. In fact, most of the workloads you see are actually relational. You just need to learn different techniques, implement the relationships between your entities. The approach is very different than designing a data model for a relational database. And if you're new to this type of database, you should definitely not follow your intuitions as to how you should model and partition data in here. Best practices in the relational world don't really translate well for this type of database, and could even be anti-patterns for Cosmos DB or databases like it. Okay, so we're going to put this into practice. I'm going to spend the rest of the session taking this relational database, the AdventureWorks database. So if you've ever used SQL Server, this should be pretty familiar. And we're actually just going to use a small part of it. This is more or less kind of the shopping cart experience here, but the tables here represent kind of the canonical workload. So let's kind of walk through what we've got. We've got our customer table. So I've got a customer table here. I've also got a customer address with a one-to-many relationship. And then I also have a third table with a one-to-one relationship, my customer password within there. And then among the product tables in here, I've got a product table, of course. And then that has a many-to-one to product category table in there. And then I've got two other tables, product tags, which has a many-to-many relationship with the product table. And then the product tag table, which is a one-to-many relationship to my product tags table. And then finally, we've got our sales order. So I've got my kind of sales order header table here, and then the sales order details. So these are all the line items from everything that's in my shopping cart that I purchased. So with a non-relational database like Cosmos DB, there isn't much we would do with this. We would never use these tables as is because the cost and performance trying to perform operations on the data would be prohibitive. Remember, we don't support joins, so I can't write queries like you would with, say, a Cosmos DB, or like I could with like a SQL server where I can join my sales order and my sales order detail within there. I would have to make multiple requests to go get the data in there. Another thing I want to point out too is that in a relational database, it's the relationships themselves are actually super critical for modeling the database itself. For a NoSQL database, this is actually just part of the story. What's actually more important for a database like Cosmos DB are the access patterns to the data. So as I go through this talk, we're going to talk about the access patterns to the data. How are we going to use it? How are we going to read or write the data? And then we'll use that to help inform the decisions on how we want to model the data within our new NoSQL database. Okay, let me have some water here. So let's talk about the operations we're going to identify here for our sample e-commerce application. For our customers, we want to create and edit a customer. And then we also want to retrieve a customer. Thing I want to point out here is that retrieve a customer is likely going to be a high concurrency operation, much more so than creating or editing a customer. So the volume of these operations actually will play a role in how we decide we want to model this data. We want to create and edit product categories. We'll also want to list all product categories. Same with the tags. We'll want to create and edit tags and list those within there as well. We're going to create a product and edit a product, of course. We also want to list products, all products from a category. And we also want to include the name of the category and then all of the tags for that product within that request, right? So that's going to be a frequently run scenario. We'll make a decision here, at least hypothetically, that customers are going to want to navigate into products by category. Now, there's lots of ways they could do it, and I don't want to kind of be exhaustive in that sense. But this would be a high concurrency operation where I want to list all products within a category. And then, of course, as I see those products, I may show a listing of those, and I want to see the tags for the products within there as well. And then the other one as well is I need to create sales order, and then I want to list all sales order for a customer. And then I'm going to throw kind of another one in here. I want to query my top 10 customers by the number of sales orders. Let's just posit that for our little e-commerce scenario, I want to do like a, I don't know, weekly or a monthly report where I'm going to query who my top customers are, and then I'm going to send them a coupon or something, or a thank you gift or whatever like that. All right, so those are the operations on there. Now, let's get started, and we're going to remodel this database, this relational database for Cosmos DB. And let's start with our customer entities. So again, I start with the operations we have here: create a customer, edit a customer, and retrieve a customer. Now, Cosmos is a JSON store. So the thing we need to do is we want to represent this as JSON within here. So I've got my customer address, and my customer password table, and we'll show those as JSON in here. Another approach we could take, because we're dealing with JSON, is we could embed these different entities into a single entity, into a single customer object here, right? Because this is what's nice about JSON is I can represent different objects within here that I can't do when I'm using a tabular database like a SQL server or whatever. So this is something we could take advantage of certainly in a database like Cosmos DB, and for other reasons I'll explain, it makes sense to do this. First of all, when I create a customer, I can now create a customer with a single insert, a single request, right? Because I've got all the data right there, and I can just do that and just do one insert and it's in there. Reading data is also easier because I only need to do a single read as well. I can simply do a query, pass in the ID for the customer, and I can get all of their data back. And that's typically when I'm going and looking up a customer, I'm going to need all the information for that customer. So it makes even more sense to want to do it all in a single request. Now you may be asking like, hey, what's the big deal whether it's a single request or not? The reason it's important, and another reason, and another kind of major tenet for why these types of databases were created, is if you go back to, say, the beginning of a relational database, relational databases has been with us since 1970, believe it or not. So 51 years, relational databases have been around. Back in 1970, the cost of a megabyte, or at least 10 megabytes, was like hundreds of thousands of dollars. So relative to compute, storage was insanely expensive. And it makes sense that the relational database and things like third normal form and normalizing databases was all there to reduce storage, right? That's why you don't see duplicate data in a relational database, because the whole purpose for relational databases was to store data and to reduce the duplication of that data, because storage was insanely expensive. Now you could fast forward like 40, 50 years, it's compute that's expensive relative to storage, right? So I have a cell phone here that costs a few $100. It's got a terabyte of storage on it. So storage relative to compute these days is insanely cheap. So the thing we want to optimize for when we're designing for a NoSQL database, and why these databases are the way they are, is we want to reduce the reliance on compute, the use of compute. And that means we want to reduce the number of requests. And we want to store data in the way that we're going to use it, right? Which is this flexibility that JSON gives us, is I can read and write data pretty much how I use it within a database like this. And I care less about the storage. And we'll talk about how other techniques we use here will help you explain that. So at this point, also people often ask, now, when would I embed data in, say, a JSON document versus when would I reference it and add it as, say, a separate row in a collection? And there's actually some pretty good rules around when you would do this. Typically, you want to embed data when there's a one-to-one relationship, like, say, customer and customer password. Also, when you have what we call a one-to-few relationship. Now, if you're asking what one-to-few is, it's a one-to-many, but it's a bounded one-to-many. For instance, the customer address, there's a one-to-many relationship in the kind of traditional SQL modeling parlance, if you will, but it's not unbounded, right? In an e-commerce scenario, a customer doesn't have an unlimited number of addresses or an insane number of addresses. They have a handful they've got themselves, maybe their mom and dad, their aunts and uncles, whatever. So that's a bounded relationship, and we call that one-to-few. The other scenario too is if the related items are queried or updated together, which makes sense, right? Because the whole point, again, is we want to reduce the number of requests. The point is any database operations are going to be fast and efficient. And if you can do them with one operation, great. So if you can embed data, do it when the related items are queried or updated together. Now, you want to reference when data is one-to-many, and that's in the traditional sense and unbounded. A scenario there would be, if I like a blogging platform. So if I had a blog platform, I may have a row, a JSON document that has the post for that blog platform, but I would not embed the comments within that document. And the reason is because, I mean, it's not infinite, but you could have a post with a few comments, but you could have something that gets hit on Slashdot, and all of a sudden you've got thousands or tens of thousands of comments. That's not going to work for a database like this. Also, if there's many-to-many relationships, those are also times when you want to reference that data as separate rows, and then you query for it together. And then the last one is if the related items are either queried or updated independently. And there's two reasons for that. One, within Cosmos, but this is true with other NoSQL databases as well. The size of the item, if you're going to do a write back on the item or say an update on an item, you typically have to send the whole payload back, and then it replaces the item in there. Now, databases like Cosmos have support for something called patch, which you can use to update a select portion of it. However, that really is only going to help reduce the payload sent over the wire. You still have to do the merge on the server side, and that's still an expensive operation. Typically, the right way to approach this is if items are not updated together, like say if you have asymmetric update patterns on your data. I'll give you an example. Let's say I've got a customer object and then I have a lat long for their position. I would store that lat long in a different row, maybe even a different container, because it's going to update frequently, whereas their name and their address and other stuff is not going to update frequently. So that's an example where I would not, and just to say, the other thing I point out too is the bigger the item is, the more asymmetric the update, the more you want to get rid of that and shred that document and have it as two separate documents. Same thing with querying as well. There's no reason, if you're querying for a large amount of data, it's just going to cost you more throughput, more compute to go and get that data. And then of course you have to send it down across the wire. That's going to add latency. So you're not going to get the kind of performance you want out of that. So those are kind of the reasons why, where you would embed versus reference within this type of database. Okay, so we've got our one-to-one relationship with the customer and the password, and we have a one-to-few relationship with the customer and the address. So it makes sense to embed everything into the same JSON document here. Now that we've defined our first entity, we're going to store this in its own container, and we'll just call that customer. Makes sense. Within a database like Cosmos, we're horizontally partitioned. So you have to define a partition key. Now you may be asking, well, what is a partition key? Remember earlier I referred to Cosmos as an abstraction over a cluster of physical servers, just like you see here, right? So when storing documents in Cosmos DB, these documents end up getting dispatched to different physical servers. And so the question is, how do I decide that this document should go to this server and that document to that server? Now, technically, we're not directly assigning documents to servers. Instead, documents are being written to different logical partitions, and it's these logical partitions that sit then within different physical servers or physical partitions up in the cloud. And so from a user's perspective, you don't really even need to think about the physical servers. In fact, this is the guidance we tell everyone, don't harbor on it or don't harp on it because it's not important or shouldn't, especially when it's a data model. You just need to know that your data is going to get written to these different logic partitions. So next, how do you decide which logic partition your data should go to? And that's the point of where the partition key comes in. So when you create a new container in Cosmos DB, you have to specify that container's partition key, which is a property that's within each of the documents that Cosmos will use to decide where your data should go. You can think of it kind of like an address to route your data to. Now, using the example above, where I'm partitioned by username, we'd end up with a logical partition where data where username equals Andrew, or a second logical partition where username equals Mark or Deborah, and so on. So there's two constraints to keep in mind when designing a data model for Cosmos DB. First is every document has a maximum size of 2 megabytes. Remember before when I said you don't, on when to embed or when to reference, you don't want to put unbounded arrays inside a single document. This is one of those reasons why, is because eventually you'll end up with the maximum size for a document within Cosmos. So you want to avoid those. This is something we're looking on increasing, but generally from a best practice perspective for this type of database, you still want to keep your documents as small as possible and keep them focused around the request that they're going to serve. You do not want to create containers with documents that have a huge amount of properties. Even if you're nowhere near the 2 megabyte size, it's still important to focus around the access pattern and the usage of that data, whether it goes into that container or into different containers or a different row in that same container, et cetera. The other thing you need to keep an eye on, and that's wrong, it should be 20 megabytes, but each logical partition is 20 megabytes in size. So you can't have more than, say, 20 gigabytes of data where username equals Andrew. So when working with data, the other thing to keep in mind is you need to, or you want to achieve an even distribution of data for your logical partitions. So if one of the logical partitions, say, gets more data than others, this is what we call a hot partition. And it's something you want to avoid. Same goes for requests as well. So if your request hit the same logical partition, this is also going to be a bottleneck and it's going to limit the overall scalability of your model. Now, let me back up a little bit. So, right, if you end up with a logical partition or a hot partition on storage, eventually this is going to fill up and it won't be able to take any more data into that logical partition. So just from a pure storage standpoint, it makes sense to distribute your data as you do writes across these different logical partitions. The other thing I want to point out too is that that's okay just for the writes, right? There's actually also reads and queries. You're actually in a NoSQL world trying to solve for two problems at once, and it forces you to think about your workload in, am I a write-heavy workload or am I a read-heavy workload? Because you're going to have to make a choice. If I'm a write-heavy workload, like say I'm ingesting IoT data, I'm likely going to want to use a partition key that's going to give me very high cardinality so that I can get an even spread of that data across as many logical partitions as possible. If I'm a read-heavy workload and I do lots and lots of queries, like order of magnitude more queries, the performance you get for queries is where you can answer those in either a single partition query or at least a bounded set of partitions, so a handful of partitions. The thing you want to avoid, well, not always avoid, but generally with high concurrency queries, is you want to avoid queries where you're not filtering by the partition key. And that's what's called a fan out query. In fact, I'm kind of getting ahead of myself here. Let me go back, let me go forward here as well. And let me talk about requests. When you are modeling, or excuse me, when you are partitioning or provisioning a container in Cosmos and you give it some amount of throughput, that throughput is evenly spread across all of the physical partitions that sit behind the logical partitions that you're going to address your data with. So what's important to keep in mind is that if all of your requests are hitting a single logical partition key, let's say they're all going to username equals Andrew, then you're only able to use a fraction of the total compute that you have provisioned for your entire container. So the Andrew partition is going to be very hot and it's going to be processing requests. However, the other ones are going to be relatively quiet. And the thing is that you will never get all of that throughput that you provision for the container to handle throughput or requests just for Andrew, because it has to be evenly spread, because they're different servers when these things are actually sitting there provisioned and sitting in the cloud. So this will so making these nice and even is going to give you the best throughput usage and best performance, and is ultimately what's going to allow you to scale, right? And is the ultimate arbiter for how you design a NoSQL database. Is that when you can achieve that even distribution of storage and even distribution of throughput, then no matter how much more data I add or how much more throughput I add, I'm always going to fully utilize that, or utilize as much as possible, and I can scale. That's the true scale out model, and it's the crux of why partitioning is so important for a database like Cosmos. So the partition partition key obviously plays a role in performance, in both the performance and scalability for your database in a database like Cosmos. So let's take example that container partitioned by username. So if we were going to issue this SQL query, select star from C, where C.username equals Mark, you'll notice it filters on the partition key property here. And because Cosmos DB understands that, it's going to send this query to a single partition. And that means that this query is always going to hit one physical server, and its performance is always going to be good. Come on, advance. Okay, so if we filtered for something else, like say favorite color here, well, we'd have no idea where the results are, right? Cosmos is just going to fan this query out to each and every logical partition. And as you've probably guessed, it's going to hit every underlying physical server. And this is this cross-partition query, or more specifically, this fan-out query, meaning that it hits every single physical partition in the database. Now, this query will work, but it's going to have an impact on the latency and throughput cost and scale. Now, one thing I want to point out is for small containers, this performance impact is not bad. In fact, it doesn't exist. If you have a database in Cosmos and it's running on 10,000 RU or less, you will not see performance impact when you write queries like this. And this is a classic trap that a lot of new people fall into with a database like Cosmos, is they assume that it works when they're doing it like this, and then they try to scale out and add more data, more throughput, and then they realize they made a mistake. And the reason is because it's not until you actually scale out the database that this type of mistake kind of rears itself. So you truly don't know if your database is going to scale until you put it under a heavy load, and a realistic load, which again goes back to why understanding your access patterns and the concurrency for that and how people access that data and the volumes of that really matters when designing a database like this. You, in fact, cannot design and model a database like Cosmos without working really closely with the solution architects or the developers within that. This is kind of another area where a database like Cosmos diverges for something like a SQL Server. SQL servers, or relational databases, you can mostly kind of design those without the need of understanding those access patterns of those workloads. Because the query engine handles a lot of the complexity, the work in there. You just need to understand the models and the relationships between the data. That's not true for a database like Cosmos. You have to work really closely with developers who understand the workload within there. Okay, so all that knowledge you now have about partitioning, we need to choose the right partition key for our customer's container. So what are we going to do? We're going to go right back to our access patterns here and figure out what things we need to do. So we need to create a customer, we need to edit a customer, and we also need to retrieve a customer. And in this case, it makes sense. We're going to look up that customer by their ID. So we're going to make ID the partition key for our container. Now, I want to point out, when you're using the ID as the partition key in a database like Cosmos, we end up with as many logical partitions as there are in the container. Each document is actually its own logical partition. Most people kind of freak out about that and they say, hey, is that okay? But it's actually perfectly fine. Logical partitions is just a logical concept. It's an abstract concept. It's fine to have infinite number of logical partitions. Functionally, this is actually a key value store, a database like Cosmos, where the partition key is actually the ID. Partition key and ID within Cosmos is always unique. So this is what you get is this key value store within there. And so I just want to point out that it's not a huge deal, and you're all fine using that. Okay, so lots of talking, lots of concepts. Hopefully you're all still with me. Let's do a demo. And here I'm going to show you some queries in the portal. As if I was going to model my data using like relational techniques. And then I'll show you what it'll look like using .NET in Visual Studio. So let's
actually, real quick, Mark, and you can stop me if you're going to touch on this later, sure. But we had one question that this might be a good chance to knock it out. So someone asked, can you modify the partition key after the database has already been created? Like suppose that, after some time, like you were talking about, you realize that there's you made a huge mistake and there's a better partition key for the model.
Great question. The partition key is immutable, unfortunately. So this is even more reason why you need to test and test under load, because if you don't and you find out in production that it's a bad choice, you need to migrate all of your data into a new container and choose a new partition key. We are working on making that less of an awful experience, I guess, or at least help bail people out a bit. We're introducing a concept called subpartitioning, which will allow you to add additional properties to the existing partition key. You can add 2 more, so you would have 3 in total, and they would be like sub keys basically. That could help with added cardinality to your key, but it may not fix it. It won't fix everything. It may. Let me take it back. It could potentially, but yes, it's now immutable, so you would have to migrate. We do have a tool to actually make that easier, a live data migrator. It sits out on GitHub. I can point people to that maybe in the chat a little bit later. I got to just look it up in there. We're also working on a tool, basically a big red easy button you can push. It's basically this code that's sitting in GitHub, but just sitting in the portal, and it can help you basically live migrate your data into a new container with a new partition key, within there. So hopefully that answers your question. I'm sure it's not the answer you wanted, but the problem is that partition key touches the physical storage, which is why you can't change it. It's why it's immutable. You have to copy it into a new container. Is there any other questions?
No, that was it for now. Thanks.
No. Okay, cool. So let me show you what I got. I got my Cosmic Works database here, and I've got 4 versions of this database that I evolve over time. That go from, this is basically the naive model here, where every entity is its own container. And then as I iterate through this, it gets progressively, see there's only customer in here, fewer and fewer, and I won't show you the last one because you're going to be blown away. But what I want to show you is, let's just say I'm going to model this in a naive way, and I'm going to run 3 queries to go get my customer information here. So I've got my first one here that's going against my customer container here. And let's see, I'm going to run that. Where's execute on here? There we go. And there's my customer object there. And my query stats, how much did that cost me? 2.83 RU. And okay, so about 3 RU. And now I'm gonna query my customer address. So I'll execute that. Terribly slow. What's going on with the portal here? Okay, it says it successfully fetched, but I don't see it. Where's my query? Or where's my data? Let's try you again. There we are. So here's my address. Here, I'm going to scroll that up. Here's my address. So customer ID, their address line, city, and query stats. That was 11 RU. So what am I at? About 11 to 3, 14 RU. And then here's my customer password query. So I'm going to run that. I don't know what's going on with this portal. They must have pushed out a new build or something. Let's do another one here. Oops. And there's my customer password, and that's also about 3. So 14, 3, 17, almost 17 RU. So, and 3 separate requests, mind you, right? So, and 17 RU. So here in my database V2, I have a customer object, and I don't have any of the others. And well, let me not show that, but what I'll do is I'll run my query here. Oh, the wrong one. Hopefully it's this one. Yep. And this is probably not going to render either, because why not? Queries. Demo gods don't like me right now, I guess. All right, let's run you again. And there we go. And here, let me make that a little smaller so I can scroll it up. And here you can see I've got my new customer object. Here's my customer header there, and I've got my address embedded in there with the location type as well embedded. And then there's my password. And I got it in a single request. And my query stats, just 2.83 RU. So the cost of the very first query we ran, minus the other 15 RU, and all done in a single request. So from a performance, from a cost standpoint, this is going to be less expensive for you. Let me show you what this looks like using Visual Studio, since this is the .NET user group. I should show you some .NET. We have a very good .NET SDK, by the way. I'm very much a huge fan of it. So let me show you some code here. So here's our query customer, and I've got a little app running here, and I'm going to run this thing, query for a single customer. So what I'm going to do here is I need to get a reference to my database. This is my V2 database that I just showed you earlier. And then I get a reference to my customer container here. I have to set this filter for my customer ID. I'm going to create a SQL query here and put a parameter in here. And then I'm going to call on the container object this thing called getItemQueryIterator. And I'm going to cast it to a customer V2 object. I should show you my models here actually. Let me define the query. And then I'm going to pass in a new query definition with my SQL, and then add a parameter with @ID, and that's going to pass in my customer ID string here. And then I'm going to call request options. And in the request options, I'm going to specify the partition key here. And this is going to help Cosmos locate the address of where that data is. Now, I don't have to specify this every time, but I like to do this best practice. I mean, it helps to better self-document the code. Obviously, hey, what's the partition key for this thing? I don't have to guess. I can look right here and say, oh, they're partitioning this container by customer or by the ID for the customer within there, right? So I can see it. And then I'm going to then do a while loop if it has more results, and then call renext async. Cast that into my customer V2 response object, and then I'm going to iterate through that and then just print that out. So that's what the code for writing a query looks like using our .NET SDK. Let me just show you our models. So, you know, what's nice about Cosmos is I can just serialize and deserialize my POCOs straight in and out of Cosmos DB. So here's my customer V2 object here. And I've got my ID, my title, first name, last name, email address, creation date. And then I have a list of customer addresses. So this is essentially my array of customer addresses. I can also embed objects, like the password is an object in there, right? So it's, here's my customer address. And then even within there, I have another object. I have the location, which is my Latin long. For my list of floats, excuse me, that are type float within there. And then password object. So I've got the hash and then the salt properties for that in there, right? So this is modeling basically your data is right here using the POCOs that define what the model for your database is. And it's done in code. It's not done in a tool like Irwin or anything else because we don't understand any of that stuff. So that's my query right here. So let's just go ahead and run this. And I'm going to run number 8 here. Query for a single customer. It's going to execute that code. And it's going to return back our customer, Destiny Peterson, that I showed earlier. And then, of course, also show that same request charge of 2.83. Now, remember before I said, if the partition key and the ID is the same, it's a key value store. Another thing you can do in Cosmos is if the ID and the partition key for any piece of data is known, and remember, partition key and ID is unique within a container. So within each partition key, every ID is unique. If they're the same, then that's the one unique record, thus it's a key value store within Cosmos. When you know the partition key and the ID for the data in Cosmos, you can do what's called a point read. Now, a point read is the most efficient way you can get data or read data in Cosmos DB. It's efficient because it completely bypasses the query engine in Cosmos. With the partition key, it goes directly to the range of partition key values that we store in the backend. And then the ID is basically the index for the data that's stored within that partition. So it's essentially going right directly to our backend store and fetching that one piece of data and returning it back. So it's insanely fast. In fact, we have an SLA on that. If you, for Cosmos users using, say, our .NET SDK, connecting in what we call direct mode, so it's a direct TCP mode, not going over HTTPS over our gateway. We have a gateway as well. If you go direct mode TCP, kilobyte of data or less using this point read is less than 10 milliseconds at P99. And at P50, it's more like 3 to 4 milliseconds and sometimes even faster. So insanely fast to read data using a point read in Cosmos DB. And here's how you would do it. You're still going to get the same database and container. And then here's your customer ID. And then I'm going to call with this function read item async on here. And then I'm going to pass in my customer ID as the ID value. And then for the partition key, I'm going to pass in that same value, right, within there. And then just print that out. I'm just going to print out the resource on here, and I'll print out the request charge. So let me show you that one here. So there. And I should have run latency on these things to show you. It's definitely faster. And it's always, for a kilobyte of data or less, it's always going to be a single read. So it's also the cheapest way to get data out of Cosmos DB. So if you have a lot of high concurrency reads, if you can model your data such that when you're doing single item lookups, you have the partition key and the ID for the data, that's a good thing, a good pattern, a good implementation to use, because it's the most efficient way you get data out of Cosmos. Okay, let's go back to slides. Am I doing okay on time, Greg?
Yeah, you're doing totally fine.
Okay, I think I may be going a little longer than I normally do, but hopefully that's a good thing. Okay, next up, let's look at our product tables here. So I've got product category. I'm going to do the same thing. I'm going to make that into a JSON document. I need to think of a partition key for this thing here. So let's look at its operations. So I need to create it and edit a product, and then I need to list all products in here. So again, I want to point out it's important to know the volume of these operations. We're definitely going to list more products than we're going to create or edit them within here. There's another angle here that it's kind of a problem. There's no where filter on this query. So how do I make this thing into a single partition query? And again, we'll look at the, sorry, I'll keep going here. So the answer to this is to use this little trick. And what we're going to do is we're going to create a new property, and we're going to call it type. And then we're going to give it a constant value for every document in our container. Now, I realize this kind of looks a little ridiculous and kind of contrived, and yes, it is in a way, but actually, there's actually a good reason to do something like this, and I'll iterate on this design a little bit later, and you'll see how this actually makes a ton of sense, and you'll say, "Wow, that's genius." So, all right, let me do another demo here. I'll query for the product categories, and then I'll show you its RU charge here. So. Excuse me, let me go back to here. So I'm going to list all product categories is my next function. Same thing, I got a query here, select star from C where C type equals category. So I now have a property here, and actually I should say that's my partition key for this thing as well. So my new query definition here, and here I'm just hard coding in my partition key of category. And then we'll just loop through the categories here, and I'll show you the request charge. So here's all my categories in here, about 37 of them within here, and pretty efficient too, just 4 RU for my request charge in here. So this is not bad. Okay, back to slides. Okay, next product tag. Same process. We're going to make this thing into a JSON document. Put it in its own container called product tag. Same operations here. We're just going to apply the same exact strategy. I'm going to put a property on here, and we'll call it type, and then I'm going to give it a value tag within there. Let's move on to products here. So translate into JSON. Next, I need to look at the relationship here to product tags. So our product table has a many-to-many relationship with our product tags within here. And I need to relay the product tags as well within here. And I also want to maybe eventually query for that as well. Now I could do this one of two ways. I could either store the product info in the product tags table, or I could materialize the tags in my product table. So now, given that there's much fewer tags per product than product per tags, it makes more sense to materialize my product tags and then embed those in my product table. Remember too, there's a 1-to-few relationship between product and tags. So this too makes it a good candidate for embedding. Excuse me, I need some water. Okay, next we'll store product in its own container, call that product. Next, we need to figure out a good partition key. And again, we'll look at the operations we need to perform. So we got to create and edit a product. But the interesting one here is we want to list all products for a category, right? And this is likely in our scenario how customers are going to search for products. So we're going to create a query like this. So select star from C, where C category ID equals, say, category A, and that'll return all products for that category. So in order to make this a single partition, we then, of course, need to make category ID our partition key for this container, and that will allow us to quickly and efficiently retrieve all products for that category. But I have another problem here is within the container, the document I've got my category ID, and then I've got an array of tag IDs. But really what I need to display is I need to display the category name that shows up in that result, right? So if I'm gonna show a bunch of products, I should have the category name at the top of the products within there, right? And also in my list display here, I want the tag names to appear as well. So, well, what could I do for that? So what's wrong with this thing? I can't make it advance. Let's try it the hard way. Okay, so in order to achieve that, I could run my query here, select star from C, where C category ID equals category A, and then go and run another query against my product category container, where CID equals category A. And then, because there's multiple tags in each product, for each one of those, I then go, for each of the products that comes back, I should say, I then got to go run this third query where select star from C, where CID is in, and then I'm going to use the in statement in there to go get all the tag names and then add them to the product. Now, I could do this, but it's not very scalable. And you may say, well, why don't I just use joins? Well, remember, we're not a relational database, right? We don't support these non-relational, or we don't support these relational constructs like doing joins across containers or anything. It's, data in this type of thing, in this type of database is really meant to be stored in the way it's used within your database and served in, ideally, a single request. So to our products table, then we're going to add additional properties, and that includes the category name here, and then also the name for each of the tags within our product item there. And so by doing this, we make sure that we can retrieve all that data we eventually need in just a single request. Okay, so let's query a product with a category name and a bunch of tag names. So I'm going to query for products by category. Is that the one I'm running here? Query for products by category ID. Okay, so I'm going to get my database and my container reference here. This is the product. And then I'm going to look up all the products in this category, components, comma, headsets. And that's my category ID here. And then here's my query that I'm going to define and create my query definition with my partition key. And then I'll just iterate through all of these and just print them out here. So query products by category ID. And there you can see, and I'll show you one of them here. The ID, category name right here. Component headsets, there's the SKU, the name of the product, the description, and then all of the tags in here. And you can see this one's got 5 different tags within here. Oh, and then there's the price. And all those products, how many have we got? 1, 2, 3. I got those back. That was 3 RU, 2.91 RU. So pretty efficient to get that all within the same logical partition there. Okay. All right. So now, when we need to create a new product, we need to populate these additional properties. But what happens if I rename a category or a tag within their 2 respective containers here? how do I manage the referential integrity between those two things, right? Because we're not a relational database. We don't have these constraints that you put on here. And we can't do these triggers. I mean, we have triggers, but they're not the same thing, basically. Well, as it turns out, Cosmos DB has a way of handling that, and it's called change feed. Now, change feed is an API that lives within every Cosmos DB container. And so whenever data is written to the container within Cosmos DB, such as an insert or an update, change feed streams those changes to an API that you can then listen to, and then use that event to respond to those changes and do practically anything you want with it. So in our case, we're going to need change feed to listen to changes that occur within the product category and the product tags containers. And then we'll write some code to then propagate those changes to our product container accordingly. Okay, so let me do a demo. Here, I'm going to query a product container for a specific category, and then we'll see how many products are in that category. I'm then going to update the name for that category, and then show you how change feed handles those changes, and then propagates them to every instance of that product in that product within that product category. Okay, so all right. So I'm going to show you a couple different things here. First, I'm going to show you the code that's going to update my product category. So this is the first thing that's going to happen is I'm going to get my category here, and it's called accessories, tires, and tubes. And I'm going to make a small change here. I'm going to change the letter or the word and I'm just going to replace it with an ampersand. Okay, so here I've got my new product category. I've got my category ID that I've passed in. Of course, it's a type category. And then here's my updated name, accessories, tires, ampersand, tubes. And then I'm going to call a function that's going to update that data. That's called replace item async in Cosmos DB. And it's pretty simple. It's on the container object. You've got replace item async. And it takes the partition key. In this case, it's the word category. Also the ID of the item. And then also the item itself right here, right? And then that's it. It's going to update. Now, the next thing I want to show you is I want to show you change feed and how that works and what that looks like. So here I've got some code here. Let me scroll this over a little here. And I'll walk you through some of these things here. So change feed maintains a checkpoint on your data within Cosmos DB. So, and it polls by default every second. And it'll say, hey, is there anything new in there? And if there is, pass it to this delegate, and then I'll do something with it. So the leases container here that I've got is essentially where that checkpoint happens, and where change feed will go and query it and say anything new. And if there is, it'll go and pass that back. And then here I've got on my product category container. So on the category itself, there's a function, get change feed processor builder. Here I'm using the underlying change feed processor. Azure Function also has these triggers you can use, but I prefer using this because this is using our latest SDK. Azure Functions Triggers uses an older version of our SDK. You get more power to do this yourself. So I'm going to give it a name here, product category processor. And then there's a delegate here that's a read-only collection cast to this product category type and passed into this input here. And then, of course, you have a cancellation token here. And then within the delegate, I'm going to create a new list of tasks, and then I'm going to iterate through each item that's passed in through that input. And here I'm going to grab the category ID and the category name that's passed in. So this is the item that's changed. It's either an insert or an update. And then I'm going to add to that task list a function called update product category name. And then I have a category ID and category name. So this is the thing that I'm going to do that I'm using to react to the data. So let me just scroll down here. Within here, I've got a query that's going to query for all products in that category, right? So give me all the products that I'm going to change, right? So here's my query definition here. And then I'm going to loop through each of those products in that product category. I'm just going to count here because I want to show you how many products it's going to hit. And then I'm going to update the product category name to the one I'm passed in. So that's the new one that got written, my products or my category container. And then I'm going to call this replace item async again, and it's going to update all the products in that category with the new name. Okay, so let me bring in this guy here. So I've got my change feed processor running here. Let me scroll back here. So when this guy fires up, he's going to write start a change feed processor, press any key to stop, and it's just going to sit there and wait. So let's update product category name. I'm going to run this here. And you can see I've got 11 product accessories, tires, and tubes. And now I'm going to update that and replace the and with the ampersand. Now look down below here, one change received and updated 11 products with the category name accessories, tires, ampersand, tubes. Here, let me scroll that out there so you can see the whole thing. Okay, so there I'm using change feed, maintaining referential integrity between two containers, right? That's the technology you can use to maintain this type of thing. In fact, change feed's amazing. There's a lot of stuff you can do with it, I know, but I'm not going to go into it here. All right, now I'm going to change it back, and let's see what happens here. Oh, I'm sorry. I just ran another query on it. I got the same 11 products, but with my new category name. Let's change it back now. I gotta hit that again. Oh, there it goes. One change received and updated 11 products back to the original product category name. Okay. So let's go back to slides. Great.
One more real quick question.
Now we're on to our last. Yep, sure.
Sorry, I think it ties in pretty well with that. And kind of going back to some of the basics here, but knowing that this is, definitely a paradigm shift from a lot of folks used to relational databases. So maybe we did have one question come in of, like why don't we have join abilities in NoSQL and in Cosmos? Why do we have to do all these change feed processes and other asynchronous processes and all that?
Right. So as I kind of mentioned at the beginning of the talk, there's a conscious decision for a database like Cosmos. Cosmos is designed to handle different types of workloads, if you will. I mean, you can use it in a smaller workload, but it's essentially optimized for performance and availability. So databases like SQL Server cannot handle like megabytes or gigabytes of data, whatever, I don't know, gigabytes, but it can't handle massive volumes of data being written at once because it's going to put locks on data when it does that. So it tends to barf and you get into much larger amounts of data. So Cosmos doesn't it's latchless in that sense, right? You just can stream data at it at high volumes. And frankly, it doesn't matter how big the volume is because in a scale, you just add more throughput, which adds more physical servers that can process more data. So that's kind of the difference. With a relational database, there's only so big of a VM you can get to. And even that VM is going to have limits in terms of connections and throughput that it can handle. And in terms of size, I think uncharted SQL can only grow to be 4 terabytes in size, and then you have to go and use like a sharded, I don't know what they call it, hyperscale, something like that. But you have to basically do the same type of thing that we're doing, which is partitioning, right? Sharding and partitioning is the same thing because you can only grow up so big to handle that sort of thing. So that's why there's no joins across containers in a database like Cosmos. Now, you can do joins in a database or in Cosmos, but it's only inside a document that you can do that. There's also another thing I want to show you too that we support that may surprise you that's very SQL-like. And in fact, I'll show you here in this in this next section, but hopefully that helps explain it. It's just this type of database is designed to scale in ways that relational databases were never designed to be able to handle. And it's why I'm not saying that you have to have a mass workload to use a database like Cosmos. It's flexible in other ways too. It's also distributed in such that it has built-in replication. and also that is designed to survive regional failures in a way that is more difficult for databases like SQL or MySQL or Postgres. When you have when you take and make your database distributed, you by definition get higher availability for that database because you eliminate the single point of failure with that. But there's other technology obviously involved in the replication for that data, and also how do you maintain consistency for that data? That's actually a whole other talk I give on how to build high availability applications using a distributed NoSQL database. Maybe when the world's returned back to normal, I can drive up to see you guys. I'll bring some stickers with me too, and have some pizza and beer with you, and I can give you that talk, I guess, when the world goes back to normal. But it's not just that reason for the high performance writes. It is one reason, but there's other reasons why you would choose a database like this, not just Cosmos, but a distributed NoSQL database more specifically. So anyway, hope that answers your question. Okay, let me get on to our last set of entities, and that's our sales orders here. So same process as before, we just are going to create JSON documents for these things. And this, of course, is another good candidate for embedding because there's a one-to-few relationship for the number of items that you're going to have in an order versus the sales order header that you have in here. And then also when you want to read the order, this is going to make for a very efficient point read. You can grab the entire contents of that order using a single request. So we'll obviously store this in its own sales order container. And then we need to look at the operations so that we can figure out a partition key. So we need to create a sales order. We need to list all sales orders for a customer. And then we also need to query the top 10 customers by the number of sales orders. Let me get to that one later. But let's talk about, we need to list all sales orders for a customer. This is going to be our high concurrency operation for our thing here. So we want to make sure that the single partition query. So we're going to partition this by customer ID here. Now, before we go any further, I want to take a little step back. When you look at the containers we've defined so far, it's interesting to note that we already have a container that's partitioned by customer ID, and that's the customer's container themselves. So what do you think? Could we store customers and sales orders in the same container? Anyone? It's hard to ask this question when you're doing a virtual thing, but when in person, I ask this question, I wait for answers. Very painful silence. Well, of course, the answer is yes, absolutely. You can mix these things together, right? Cosmos is schema agnostic, so this is actually something that's completely supported in a database like us. And in fact, it's actually a best practice for a database like this. It's suitable for different entity types when they share similar access patterns, and for sure, customers and sales orders share similar access pattern. I'm going to log in as a customer and then retrieve my sales orders within there. So, and of course, they share the same partition key. So if these two conditions apply, this is absolutely something you want to do. In fact, it's something you really should do because if you can combine them into a single container, they can share the throughput that you provision in the container. So you're going to get overall better efficiency within there. So instead of storing these in their separate containers, we're going to merge them into the customer's container here. I'm also going to change the partition key from ID, and I'm going to make it customer ID. And then I'll add for the customer document itself, the ID and the customer ID is going to be the same value. Okay, so then each of the sales order, of course, is going to have its own ID value. Now, next, I need to be able to distinguish sales orders and customers within the same container. So I'll add this additional type property that has a value of customer for the customer objects, and then sales order for each of the sales order. And I can query for this separately then if I want. Now, I want to point out something. I've just been calling this the type property. This actually has a more official name. It's really a discriminator property is what this is really called. And as the name kind of implies, it helps you to discriminate between different types of entities that are stored in the same container. Okay, so now what we have is a container where each logical partition is going to contain exactly one customer record and all that customer sales orders here. So now if I want to get all the sales order for our customers, I simply run this query. Select star from C, where C customer ID equals customer A, and C.type equals sales order. Okay, so let's see what that looks like. Go back to a demo here. And whoops. Yeah. Sorry. And okay. So query sales order by customer ID is the function I'm going to run here. So here I'm going to get my database, my container. Here's my customer ID. Here's the query I showed you earlier, right? So use the discriminator type properties for sales order. And then here's my query definition. And then I'm just going to print this out and loop through each of the sales orders here. So we'll run that F. And here you can see I've got one order here. It's just got a product, this, and here's another. There's only 2 sales orders for this person. And this one's got 3 products in there. Okay. So I'll keep trucking along here. I don't want to keep you guys too long, but we're almost at the end. Finally, I want to look at the last request we're going to serve. So we want to query our top 10 customers based upon the number of sales orders they've had. And this requires you to count the number of sales orders for each customer, and then sort those counts in descending order, and then return the top 10 of those. So even though customers and sales orders now sit in the same container, this query is actually not one I can do, at least currently with Cosmos DB's query language. So once again, I need to denormalize the data within here, which is another very common technique for data within a database like Cosmos DB. Is, of course, you want to denormalize data. We don't care about eliminating duplicates. In this case, I'm going to denormalize an aggregate. And that aggregate is the count of the sales orders within each of the customer entities within here. So what we want to achieve is that every time I add a sales order to the customer's logical partition, I'm going to update that customer document and increment the sales order count within there. Now here, we can benefit from the fact that each customer and sales order sit within the same logical partition. This might surprise you, but Cosmos does actually have support for transactions. But these transactions have to be scoped to the same logical partition. So I could do transactions for the customer and all the sales orders for that customer in this container because they sit within the same logical partition. And there's 2 ways you can do this in Cosmos. You can use what we have are stored procedures. These stored procedures are not like SQL stored procedures, are actually written in JavaScript. Or if you can use, if you'd like, and I prefer this, and I'm going to show it to you, a new feature, relatively new feature in our SDK called transactional batch. Okay, so this would be the query we could run now is select top star from C, where C.type equals customer, order by C.sales order count in descending order. So that's the query that's going to satisfy that. All right, so I'm going to show you a bunch of stuff here in my last demo. Let's go to, whoops, what was that? All right, so I'm going to show you this function here. I'm going to create a new sales order and update my customer order total. So I got my database. Here's my customer container. Here's the customer ID. Now, the first thing I'm going to do is I'm going to read the customer record in. So I'm going to call my read item async. And then for my customer object here, I'm going to increment it by 1. So I'm going to say customer.salesorderCount plus plus. And that'll increment whatever's there by 1. Next, I'm going to create a new fake sales order ID here. You'd normally just new up a GUID, and at least in this system you would. And then here's my new sales order object here. I got order date, obviously nothing for ship date because it hasn't shipped yet. And then I'm going to add new order items in here. I've got a mountain bike frame that's black, 38 inches, and a pair of racing socks. And then I'm going to use this fancy function called create transactional batch. Now that sits off the container object here, and it takes a partition key, which of course, as I said, everything's scoped to a partition key. So that's the customer ID that we're using here. And then I can call multiple items within here. I can call up to 100 actually operations within that same logical, within the same transactional batch. within here. So I'm going to do two things. I'm going to create my new sales order item that I created up above here. And then I'm going to call replace item on my customer object and pass in a customer ID and then my updated customer object with my updated sales order total. And then I'll call execute async on that. Okay, so let's create new order. Actually, I'm going to query for customer in all orders. Let's do that one first. So here's my customer, and I got 2 orders for this customer in here. Now I'm going to create a new order and update the order total. So that's that function I just ran. And order created successfully. All right, so now let's query for that customer in all orders. And I've got there's my new order. So here's my first 2 here. And here's the new order where I've got my mountain bike frame and my racing socks within there. Huh? Awesome. Okay. Now let's query for our top 10 customers, because I'm now, if I show, where is it? Oh yeah, here, sales order count right here, right? So that's the property I'm now able to query using my new query for my top 10 customers. So go ahead. All right, so now I'm going to query for top 10 customers. That is, where are you? This one here. So select top 10, first name, last name, sales order count from C, where C.type equals customer, right? I want to filter for just the customer object, and then order by the sales order count descending. So query for top 10 customers. And there you have it. There's my customers and their orders within here. Okay. By the way, so I can use that transactional batch not only to like increment stuff, but I can use it on deletes as well, right? So I can do the same thing, call customer sales order count, minus, and then do another create transactional batch, delete the order ID, and then call replace item on my customer object, right? So I can go ahead and do delete order, update item total, and then query for my customer and all their orders again. And you can see, if I go to sales order count, it's now back to 2 for that customer. So I've functionally run that as a transaction within there. So let's go back. Almost done. Almost done. I know you want to get to beers or whatever, I guess, virtual beers. So I don't know if you noticed, but this last query is actually cross-partition. Now I know I said you want to make sure that you're answering your queries that are in partition or a bounded set of partitions. This is true for high concurrency queries, but if you're running a query like that's once a week or once a month or something like that, the low volume queries, those are okay. Typically, it's not worth pursuing making everything single partition. And this is something, understanding your workloads, not just the access patterns, but the volume of these patterns or these operations is important, because you need to understand the cost that it takes to run the operations and know if you need enough throughput to be able to do them. So, queries like this that get run once a month, that's usually not a huge deal. So that's our new query there. Not going to demo this. And so here we're looking at our near final design. So we've gone from 9 tables down to 4 containers in here. Another thing too is I can actually take and merge my product tag and product type. If you notice here, they've got the same partition key, it's type, right? So no reason why I can't merge those even further and put those into a single container. In fact, this is another best practice for a database like Cosmos, is if you have like master data, reference data like this, put it all into the same container, and then just use a discriminator key like type, and then you can go and just, efficiently store that data in there. Just make sure that it doesn't grow any larger than 20 gigabytes in there. So here's our final design. So we've gone from 9 relational tables to 3 containers within Cosmos DB. And this thing is designed to scale. You can grow to infinite size with a design like this for our little e-commerce application here. And it'll do so efficiently. within there. So let me move you past the key takeaways. Well, let's talk about it. So basically, takeaways, identifying the key access patterns is hugely important for this type of database. Relationships are just the start. You have to know how people access the data, how your app uses it to be able to design efficiently. Partitioning is absolutely critical to making sure this thing scales. It's horizontally partitioned, or it's horizontally scalable. So you have to know that key so that you can, scale out efficiently. Materializing relationships, whether you're embedding, whether you're denormalizing and pre-aggregating, or storing related entities in the same container. These are all techniques and concepts that are important to modeling data to be efficient in a shared nothing database like Cosmos DB. And then the different methods needed to do and maintain things like relationships, using change feed or using stored procedures or transactional batch to denormalize aggregates like that. So going further, here's just some links. All the stuff I just showed you is on a GitHub repo, github.com/Azure Cosmos DB/CosmicWorks. I'm currently working on building a data loader for this thing, but all of the data is sitting up there. All the code you just saw, all sitting up there. If you want, you can download everything or clone it all now. You can write your own data loader and load this all in. There's an ARM template that'll create all the accounts for you. So feel free. We just recently, if you don't want to do all that work, we also just recently released this as a set of Microsoft Learn Labs. So you can go and walk through the concepts here. This costs you nothing to run, by the way. It all runs in a sandbox. The downside is that you don't get to take it with you on there. So if you want all the stuff, all the code and everything, just go to the repo. Or maybe clone the repo and then go take the lab. Might be good. More links there. We got lots of awesome videos on YouTube as well. I run a weekly podcast called Cosmos DB Live TV, where I interview and just talk with various people, well, all on our team, but also just people in the community as well. So feel free to come in and join. That's Thursdays at 1 p.m. And you just go to cosmosdb.com/TV. That's it for my talk. Sorry I went over. I don't I don't know if people stuck around or they just said this guy's taking too long. I'm going to go off, drink some beer. I don't know.
No, folks still stuck around. We've actually got at least one question sitting there now, and another comment that came in just as I was saying that was so good. So you've got an active audience for you. But we do have one question here saying, can you change an ID within a partition key? So like, is it possible, to do that with the replace async call that you showed?
You cannot change an ID. You can add a new item and then delete that one, but you cannot update the item. You can't update the item's ID.
Gotcha. And one more that just came in, is there a way to test Cosmos DB locally, or can it be tested only with Azure?
No, in fact, there is both a Windows emulator that we've had forever. We also just announced a new Linux emulator, actually, that runs within. You can actually just do a Docker pull, and it's up on the Docker registry. That just is for SQL API only. I'm sure if you just go to our docs and just kind of type in emulator in the top left search bar. Here, let me see if I can quickly get you there. Of course, that comes up for me because I'm in here all day. Emulator. So there's install and use the emulator and emulator on Docker. We got two images. There's a Linux one and a Windows one. But anyway, lots of stuff for you there. We also have a free tier, by the way. Good for that. You can have one free Cosmos DB account per subscription. So if you got multiple subscriptions, party on. That's good for 1,000 RU and I think 20 gigabytes of data. We just recently announced increased amounts on there. We also have a serverless option too, by the way, which is really helpful for dev test. Right, we're a provisioned service, so like a VM, if you're not using us, we're still sitting there spinning the wheel. So, but serverless is, of course, serverless. It doesn't cost you anything if you don't do any operations. So that may be an option for folks that wanting to do like just dev test in there. You can't really, also unlike a VM, you can't stop and deallocate the VM and so back and start it again. We're not quite like that. We're a multi-tenant service, so you're either using us or not using us. But we do have options for tier, emulator, serverless. So we're trying to be flexible in how you can use this and try to make it as painless and easy as possible, and for you to test the waters and try it out.
Awesome. Well, at least currently that was the last question that was in there, so I can start a sort of closing spiel and see if anyone kind of sneaks a new question in before I finish. But first, just want to say thanks, Mark, for going through all that. That was a pretty awesome set of demos and a lot of good content for folks. Thanks everyone for coming and hanging out and asking a lot of really good questions. To what I was saying at the top of the meeting, that's what makes this fun. To have folks showing up and being engaged and all that. So really appreciate all that. We'll have the video for this up in the next couple of days. Look out for a link on our meetup page and Slack, on Twitter, all the usual places. We'll get that up. But yeah, thanks again, Mark. This was really, really awesome.
Well, thanks for inviting me. And like I said, I'm semi-local. So, provided that the 405 is not a complete disaster, I'm happy to make the drive up to West LA or wherever you guys end up starting it up again, and coming and seeing you guys. I'll bring some stickers, maybe some other stuff. I don't know. Once things are physical again, things like swag become like I got to go back to my marketing person and ask for I got to ask him for some money so I can go and do stuff. So yeah, it'd be great. I'd love to come up and see you guys in person sometime.
Absolutely, we will 100% take you up on that offer across the board.
Cool.
But in the meantime, thanks again for the awesome session, everyone, for showing up. Keep an eye out for some upcoming meeting announcements, both virtual and in person. It's awesome to be able to finally say that again. But in the meantime, as always, stay safe and healthy, and we'll see you soon. Have a great night, everyone.